It's not showing up. Yeah, thanks, Jack. Cool. Was that all I want to say? Oh yeah, David just have one more thing. Like, he's probably not going to ask you to do something like UART, like something that you've really only covered very theoretically in the lectures. So those communication protocols, you're probably expected to know of them, but you're not going to expect it to really answer a crazy question about them. So don't get too caught up on, you know, trying to get on top of what UART does and that sort of thing. More focus on assembly programming, understanding what the instructions do and the limitations of those instructions, which is what I'll also focus on in the crash course. Cool. Yeah, for those who just joined, there's a document in the chat that you can use, which is basically what I'm going to be filling out. If you don't have access to it, let us know. We just send it again. Cool beans. Okay. If there's no special requests, let's get started. Oh, before that, so there's some ELSOC resources here. So that's all past papers and stuff. There are 2-on-4-2 past papers, so they're going to be more theoretically based and practically based. So cherry pick the practical questions out of those ones and ignore the content that you haven't learned. The other thing is, like, there's some extra coding exercises on Moodle. One of these, I think it's the old Lab 3, has quite a lot of like small kind of coding problems for you to work through. So that's kind of nice. Cool.
Is that like practical living, like this?
Pretty much, yeah. So you'll also we'll do some number problems as well, like converting bases and that sort of thing. But yeah, I think a large portion of your exam will be coding.
What does like subroutine?
What does subroutine mean? That's a good question. So you know how, like, in the labs, when you would branch to a particular label and that label would do something and then you'd move back to where you were? So that label represented a subroutine. And so it's basically just a routine that you jump to, you do something, and you go back to what you were doing. So subroutines are just small sections of code that like that. You can think of them like functions. Yeah, they're like the assembly version of functions. Yeah, make sense? Yeah. Okay, cool. Let's get into it. So the 7 processor modes. Does anyone want to have a guess at any of those 7 processor modes? User, yeah. Any other thoughts? Type in the chat for those of you who are online. So system, yeah, yeah, yeah. We've got a system. Cool. 3 more. Abort, undefined, yep, and SVC, which is like, yeah. So what do they all do? What do they all do? User, where your application runs, so that's where you do stuff as a user, and it doesn't have very many privileges. So this is the only mode that is not privileged. The rest of them are all privileged. FIQ handles fast interrupts. And so FIQ and IRQ are your 2 interrupt modes. The difference between FIQ and IRQ is that FIQ is for fast interrupts. So they're really important ones. You generally only have one of these interrupts. And so all the other interrupts would be just IRQs, which have lesser priority. So they're both interrupts. They're both privileged. So important interrupts and other interrupts. Cool. What about system? So system is just like user mode, but with privileges. So you can just do more stuff. And abort and undefined. So abort handles memory access problems. So if you do something silly with your memory accesses, you probably jump into the abort mode so that you can handle that. You can think about that like a segmentation fault in C when you dereference a null pointer. So the abort mode is used for those sorts of things. So handles memory access. Oops. Undefined. So it handles undefined instructions. So ARM's actually really cool in that you can actually define your own instructions. And yeah, it's a little bit weird how it does that. But point is, if you type an instruction that is undefined or doesn't make sense to the processor, that's what the undefined mode is used for, to handle those sorts of problems. Cool. And SVC is a special mode you're entered on reset and software interrupts. So it's just used for those two. Cool, and we'll talk more about interrupts a bit later on. Cool, so they're the 7 processor modes for the ARM architecture that we're dealing with. Probably a good point just right now, right at the very beginning, to just remember why we have a 3-stage pipeline. So can anyone remember why we have a 3-stage pipeline? Yeah. By splitting up into 3 parts, you basically, the time to execute instruction becomes the maximum of those 3 sections. And you can imagine if you split up into more stages, then you get a faster throughput, but your system becomes more complex. So yeah, faster throughput. Cool. All right. So a little bit more theory. The 4 instruction categories. Can you remember what the 4 instruction categories are? I'll hit you off. Data. So data is one of them. So data processing instructions. Or data transfer, I should say. So these are ones like, for example, load and store. So loading and storing to and from memory. Okay. Another one would be control flow. So these are like your branches and your, branch and link, etc. Thirdly, you've got data processing. So data processing is stuff like your add, subtract, everything you do, stuff with actual data, like, or whatever. Cool. And the last one we call special. And that's for some really weird instructions like MSR and MRS, which are used to basically do stuff with the program status registers. So copy the status registers into registers and then go back the other way as well. Cool. So there are 4 instruction categories. All right. Enough theory for a second. Let's do some actual example of something. So you do need to know base conversion for the exam. And so let's convert this base 7 number, 63.124, to a base 9 number, and just kind of remember how this sort of works. So So for a base conversion like this, when you're going from a base that you don't really know to another base you don't really know, it's quite difficult to do that conversion. Now, you can say you can just do this on your calculator, and that's fine. But in the exam, if you get a question like this, they're going to ask you to show you working. So you can't just say, I use your calculator. So you know how to do it. The easiest way to do this is like to go from this to a base 10, so decimal, to a number that you actually understand. And then to go from your base 10 to the destination base, which in this case, we're going to base 9. If you try to go from 7 to 9, it's just going to get really complicated really quickly. So how do we go from base 7 to base 10? Well, I think the first thing to remember is that like each of these things just represents like 7 to the power of something. So this is 7 to the power of, 0. That's 7 to the power of 1. And this is 7 to the power of -1, which is the same as saying 1/7. And this is the same as 7 to the -2 and 7 to the -3. And so in decimal, the value becomes 6 times 7 to the 1 plus 3 times 7 to the 0 plus, well, let's just do the decimal part first. Sorry, the integer part, because that's kind of nice and easy. 6 times 7, 42, plus 3 times 1 is going to be equal to 45. So it's going to be 45 point something. And so then we've got this decimal part here, the 214. And this gets really messy now. So this is probably where you'd like to get your calculator to work out what the actual decimal part is. But we've got, we've got 2 by, well, it's really just 2/7, isn't it? 2/7 plus 1/49 I think I might just siege the 4 at the moment because that's going to be really complicated decimal as it is. And so if we work this out on a calculator, does anyone have a calculator? 2/7. Oh, we can do this now in heads, surely. 2 times 7, 14. That's just, oops. 15/49. So what's 15 divided by 49? 306. 306. Cool. All right. And so on. Let's just approximate to that. So the decimal value is 45.306. And then if we're going to go and translate this to base 9, we would just kind of do everything in reverse. So in terms of 45, we would just break it down into powers of 9. Now I can probably logic this and say that, well, this is just what 9 to the power of 1 times 5 plus 0 times 9 to the 0. But we can do this more mathematically by dividing by 9 over and over again until we get to 0. But anyway, I'm just going to kind of go with this because it's nice and easy. And you can have a look at the worked examples in your the notes for a more rigorous way of doing it. So this is just going to be in terms of base 9. It's just going to be equal to the decimal part is going to be 50. And so the integer part is going to be 50. And then the fractional part, we take 0.306. And what we do is we keep multiplying by 9 and taking the integer part. So I might just kind of move this up a little bit. It's going to work. Oh. Not work. Just grab this then. That works a little better. Cool. So let's do this in blue because this is probably the more tricky part of it. So if we take 0.306 and we multiply by 9, then that's going to give us, well, I'm going to write it down here, but I should get a calculator at this point. That's going to give us 2.7, actually no. That's going to give us 2.754. And so what we do is we kind of just look at the 2 here, and then we grab the other bit, the 0.754, and we multiply by 9 again. So what we're going to get is we're going to get like an accumulation of the integer parts of these multiplications. And then we're going to get these integer parts and just kind of shove them together to make the decimal. So if we get 0.754, and we multiply by 9 again, then we get 6.786. And so on and so forth. And so we could keep going onwards and onwards into infinity. I'm going to do the three decimal places for this one, though the question should specify exactly how many decimal places. So I'm going to take 0.786, multiply by 9. That's 7.074. And so what we do is we just grab these 3 integer parts, the 2, the 6, and the 7. Cut them there as our decimal point. So that's how that one works. Now, obviously, base 9 is not going to be, base 7 to base 9 is not going to be very nice. The way to remember like how to do this is like where do I put the 2, the 6, and the 7, or should it be like 7, 6, 2? The way to remember this one is like if you're multiplying by 2 and you had like, I guess, like if your fractional point was 0.5 and you're going to binary, you would multiply by 2. Eventually, you're going to get 1.0, right? And so eventually the fractional part is going to be 0. And you're going to have 0 multiplied by 2 equals 0. And then so on and so forth if you continue this algorithm. So that would lend itself to being like 0.1000 because adding zeros to the right-hand side doesn't make any difference to this as a decimal. Anywho's, yeah. So that's how you do that one. Is there any questions about base conversion in general before I move on? It's just something that you got to practice. So there's stuff in the weekly questions that David put up. But yeah, any questions, people online or no? Cool, awesome. I'll give you access to this later as well. Cool. All right, so we should probably talk about some assembler directives and what they do. And then we'll have a look at an example with a line, because I know a line is something that trips a lot of people up. So we'll start with DCB, DCW, and DCD. So what do these three things do? Well, they all allocate some sort of space. DCB allocates a byte. DCW allocates 2 bytes, and DCD is 4 bytes. It's a little bit weird because how much space are they allocating? Oops, yeah, that's fine. What does W and D stand for? W stands for word, but usually we'd say word is 4 bytes. Well, because the ARM architecture has the 16-bit thumb integrated with it as well, therefore we define like a word as like 16 bits. So that's why a word is 2 bytes or 16 bits in this case. And a DCD is like, D is like for double, so double word, so twice as much as a word. Okay, hopefully you're all familiar with that from the labs. What's possibly not so familiar is how we use a line to do stuff. So a line is basically something that we use when we're using DCBs and DCDs to place the next instruction or memory allocation at a specific point in memory that we desire. So for the align expression offset, what this really kind of condenses to is find the next spot in memory of the form n multiplied by expression plus offset. To see exactly what that means, you should probably just have a look at an example, and then you guys can ask me questions if you're confused. Let's have a look at this one. So we've got some code here. We've got this stuff, some DCBs, and then we've got an align. So if we were to work out what this looks in memory, let's just type out the first 3, which is a DCD and 2 DCBs in memory, and see how this actually looks like. So the DCD is going to occupy 4 bytes of space, and that's going to be these 4 here. As to what values are in these 4 slots, remember, we're assuming little endian here, which is what your processor usually is. So if you don't hear otherwise, it's probably little endian. And so what that means is that the lowest byte goes to the lowest memory address. So the 15 will go to this memory address here, which is the 4000. 4001 will then hold A3, which is this 2 here. So pop those in. And then the rest are going to be 0 because the last 2 bytes of this DCD are going to be 0s. So looks like that. We then have 2 DCBs. So DCBs, they're easy. We just chuck them one after the other, 2, 2, and 4, 4. And then we have the align. So what does the align do? It tells us where exactly this next DCB should start from. When we have the align 4, 3, remember that align means finding the next spot in memory of the form n times expression plus offset. So in this case, we're looking for n times 4 plus 3. So we look at all our memory addresses, and probably the easiest way to do this is to start with the expression part of this, so the 4. When we have the 4 here, that's n times 4, which means that like we need to have some sort of multiplier by 4. So every address that is a what is it? Every address that that can be, I don't even know what the word is for this. Every address that is divisible by 4 is what we're after as a base, and then we're going to add the offset to it. So let's go and bold everything that is divisible by 4. So that's going to be basically everything that's here. What have we got? No more. Cool. So these bold addresses are the ones that are multiples of 4. So this represents the n times expression part. Now, when we add the offset, we're just going to add 3 to all of these ones. So I might just represent them by highlighting them in red. So if I add 3 to one of these bold addresses, for example, this one here, then I'm going to get the 3 over here. And so this is a possible candidate for the next spot in memory to write to. So we've got 3 of them because we add 3 to each of those bold addresses. Now that we've calculated the possible ones that are of the form n times expression plus offset, we need to choose the next one that's following the current free spot in memory. So, well, the last written spot. So this was the last one that we wrote to. So we're looking for something after 400005 that fits this criteria. So one of the red ones after this spot. And we can see that the next one that suits is going to be 7 down here. And so our 0x72, which is the next DCB in our short section of code here, is going to end up corresponding to this red dress here. And then correspondingly, the 11 is going to end up there. Does anyone have any questions about how a line works and the idea behind n times expression plus offset? If you're online, feel free to chuck in the chat. A short note, if we get rid of the offset, then it's just n times expression. We just don't add any offset to it. And this can be like anything you want, right? Like, so just don't get tripped up by that. If you don't have anything, just having a line, the align will just, it's the equivalent of saying align 4. So it aligns it to like a 4-byte boundary. Can anyone think of any reasons why we would want to align specifically? Like align 4-3 is pretty silly. I've never seen that used anywhere because who wants to align to, you know, a multiple of 4 plus 3? But in terms of like aligning in general, particularly align 4, can we think of any thoughts? Sorry. Yeah, maybe. I have to think about that, but that's possibly, yeah.
That influenced our instructions at 32-bit, which are for
Yeah.
4 lines.
Yes. Yeah.
So by natural, want to have some sort of alignment.
Yep.
So that they are kind of padded.
Yep.
Into a multiple of 4.
Yeah. Yeah. That's pretty much correct. Is that what you're going to say? Yeah. So we want them to be, the instructions to be aligned. So the problem is if I had, if I then went and put like an instruction after here, so with our 4-3, and I went and then put an instruction down here that was like, I don't know, some sort of add, it doesn't really matter what it was doing. We can see that the add is going to be spread over like these 3 plus the next one that doesn't start at a multiple of 4. Why is that a problem? It shouldn't be. I mean, our program counter is, you know, it does its own thing, right? It pluses 4 every time, right? So it should be able to index memory at a particular place. Except if you go and try and branch to, so if you try and use like at some point, if you use a branch like a BX to like this, if this had a label, hello, do hello. BX is branch and exchange, and what it will do is it will move you into the thumb mode if your address that you're going to is odd. So you can see that like this would correspond to this address here for the add, which is odd because it ends in a 9. And so as a result, you're going to swap from ARM to thumb mode. So thumb's the 16-bit version of ARM, and that's just going to screw with your program. So we'd need to have this aligned there so that your program works the way you want it to, and specifically so that your instructions are 4-byte lines. Yeah, cool. So if there was no offset, would the DCB 0x72 store in 0x40008? That's a good question. Let's have a look. So if there was no offset, then we would align 4, which means we'd choose one of the bold addresses, right, Wilson? So that would mean that, yes, it would go to, the 08. So basically that would look like there, and that one would go down there. That's correct. Yep. Cool. Awesome. Yep. Well, you can think about it as adding some sort of padding to your memory, right? So it will affect the next one, and obviously everything following on from that. So just insert some variable amount of padding based on what you want.
But the ones before won't be.
Yeah, ones before won't be. Yeah. Does that make sense?
Yeah.
Cool. Awesome. Let's put that back so that it's like the original example 3. Let's get rid of this guy. Cool. Okie dokie. So multiplication via shifts and adds. We've done a little bit of this in the lab, but it's probably good to come up with like a rigorous way of doing this. So does someone want to give me a random 3-digit number? 712. Okay, that sounds good to me. So what we want to do is we want to do like some variable x multiplied by 712. So let's assume that that x is in, let's just say, register 0, and we want to perform x times 712. I'll make it a little bit bigger for the people. Whoop. Yeah, cool. Yeah, so let's do x times 712. Now, we've learned in the labs that multiplication is expensive, particularly big numbers, so we want to try and do it with shifts and adds if possible. So how do we break up this x times 712 into shifts and adds? I think in the lab we multiplied by 10, so that was really easy. You could just do it in your head. But how do we do it for a bigger number? Well, what we need to do is we need to kind of break it up into a series of x multiplied by something plus x multiplied by something else, and so on and so forth. And the easiest way to do this is to look for, because remember that like with a shift, when we shift like left by 1, we multiply by 2, right? And so this is why we want to break it up into shifts. So if we can break it up into a sequence of multiplications such that each of these somethings is a power of 2, then it will naturally convert to a series of shifts, right? So the first thing we want to do is we want to look for a power of 2 that's really close to 712. It's probably a little bit easier to go from underneath than to come from above, because then you can use addition instead of subtraction. So let's start with that. So the closest power of 2 I can think of to 712 is 512. So I'm just going to chuck that here. And so what I'm going to do is I'm going to say that x multiplied by 712 is equal to x multiplied by 512 plus. Now, if we've got 512, that leaves us with like 200 remaining at this point. I'm going to put that like over here. So we've got 200 remaining that we need to do. Closest power of 2 to 200. Well, if we go underneath, it's 128. So we're going to do x multiplied by 128 plus. So let's take away 128 from 200. That would give us 72. And so 64, I think, is the next one that we need to do. And so that will give us, what's left after that? 6 plus 2, 8, I think. Yep. And so then that's just x multiplied by 8. Cool. So because 712 is 512 plus 128 plus 64 plus 8, we can break x multiplied by 712 up into this sort of multiply and addition. And we of course know that x multiplying by 512 is the same as shifting x left by 2 to the power of whatever it is that gets to 512, to the power of 9 in this case. So what are we actually going to do? I'll just put that in comments. So, we won't do that. Anyways, so let's just write some assembly code to deal with this sort of problem. So what that would look like is if we assume that x is in R0, then what we want to do is probably don't want to touch R0, but we want to accumulate stuff into R1 perhaps. So if we add into R1, what have we got? R0, LSL. Oh, I think we need to probably start this off by just starting R1 with 0, and then we go R1 and LSL hash, well, 9. So this is going to be the 512. Cool. And then we're just going to kind of do this multiple times, right? So we're going to do a shift with 2 to the power of what equals 128? 7, I think, from memory. So we're going to 7, so that's going to be 128. 64. What's 2 to the power of what is 64? 6. Yep. And then for 8, that's easy. That's just a shift by 3. And then by the end of it, we've got our value in R1. And of course, we could then go and move into R0, R1 so that we can return this value if this was a particular subroutine, then we're following the AA PCS. But yes, so that's how we would break it up. Any questions about that? So in summary, break up your multiplication into additions of powers of 2 and go from there. If we had chosen a number instead of 712, if we'd chosen something like x multiplied by 511, we can see this is going to be a pain because it's going to be every single multiple of 2 up to that. It's like 1 less, right? So in that case, we could do a little bit sneaky and we could be like, okay, well, that's actually x multiplied by 512 minus x multiplied by 1. So sometimes it's just a lot quicker to look at the subtraction side of things. And this involves, from memory, it involves the use of like the reverse subtraction operation. So you'd have to just have a think about how you'd use that in that case. What do I want to say? Yeah, as a general thing, if you're happy with using this sort of stuff like subtraction as well, a good strategy is to choose the power of 2 that is closest, either above or below. And then keep going that way. And you'll either do a series of additions or subtractions in order to get to where you want to go. Cool. Any questions about converting like this sort of multiplication to shifts and adds? No? Sick. Awesome. Alrighty. Pre and post indexing and how they work. So pre-indexing is where we add so this whole thing, pre and post indexing, is to do with memory access. So when we talk about that, it's like when we do a load or a store. And with the pre and post indexing, it's all to do with adding an offset onto a base address that we have. For example, you would remember probably doing this quite a lot, something like LDR, R0, and then you've got PC hash 20 or something for a certain offset in the labs. And this is a form of memory access that uses the form of indexing. In this case, we used pre-indexing because we added the offset to the base register, which was the program counter. So in terms of what these are, destination register is R0, program counter represents the base address, and this is our offset. Then what this does is it actually computes PC plus the offset before it goes and accesses the memory. So this particular thing is a form of pre-indexing. Cool. With pre-indexing, because we add the offset before, we have an option to either update the base register or not to update the base register. So when we have the PC offset, we don't usually want to update the base register because why would we want to change the PC? But if we are accessing an array, for example, and the base register for your array was R1, and you wanted to just increment it by 1, then you possibly would want to update, and you update by putting an exclamation mark at the end, if I'm correct. Yeah, so that's pre-indexing. It's all about adding the offset on before. What's the opposite of pre-indexing? The opposite is post-indexing. And post-indexing is where, instead of adding that offset on before, we add it on after. What does that look like? It would look a little bit something like this. So using the same sort of syntax as before, you can see that the offset is now outside of those square braces and just chills at the end there. So what that would do is add the offset on afterwards. So you would load from R1 and then you'd perform R1 plus 1. Now, if we think about this, the offset only gets used after we do the load. And so there is no possible use case for us not to want to update the base register. If we didn't want to update the base register with a post index, we would just get rid of that, right? So post indexing always updates the base register, in this case R1. So the sequence of events here is that R0 will get loaded with the value at address R1. And then we will do R1 is equal to R1 plus 1. So that's the sequence of events for post-indexing. Any questions about pre versus post-indexing and the idea of updating the base register after? Yep.
So what's the difference between saying that's free while updating the starting at different?
Yes. Yeah. So just bear in mind that, like with pre-indexing, the offset gets added on before you do the memory access. And with post-indexing, it gets added after. Does that make sense?
Yeah.
Cool. Awesome. All right. So now that you know what pre and post-indexing is, let's have a look at an example. So we've got some code here that does a whole heap of loading. And the question is, which registers end up being loaded with 42? So have a second and have a look at the code. I'll give you a minute to read through it, and then we'll talk about what it's doing. Okay. Hopefully you've had a bit of a look through. So let's talk about what the code's doing. Does anyone have any guesses first as to which registers get loaded with 42? R1? Just R1? Cool. That's fine. Yeah, let's talk through what actually happens here. So the first thing we do is we load the base address 4000, which just represents this kind of point of memory here, into R0. And then secondly, we do a pre-indexed load. So this means that we compute the offset first. So R1 gets loaded with R0 plus 4. So if R0 is 0x4000, the 0x4000 corresponds to this number here. And when we add 4 to it, that increments it by 4 bytes. Remember, a DCD is 4 bytes, and so we jump over to this one here. So R1 gets loaded with 42. So let's go and type that down here. So R1 is equal to 42. Okay, but remember we got the little exclamation mark here. So really, as well as R1 is equal to 42, R0 also gets updated to be R0 plus 4. And so that's just going to be 4004. Then what we do is we do a post index. So remember, we ignore this offset until after. And so what that means is we load from R0 first, then we do R0 plus 4. So R2 just gets loaded straight from R0. And because R0 represents 4004, it's just going to jump straight to the 42. So on the second load, R2 gets loaded with 42. And then R0 equals 4008. Make sense? Cool. Any last questions about post and pre-indexed loads? Make sure you cross these, just because if they give you a question like this, it's always nice to understand what's going on. Yep. No, I'm just, I should probably replace it with a label, make a comment that it's address 4000. Yeah. I think it will give you, the labels, I believe, have to start with a character, not a number. And so, yeah. No, oh well, that's all right. Fix that later. Okie dokie. There's no other questions. Awesome. Endianness. So endianness is how things are stored in memory. You need to have a consistent endianness for your processor, otherwise it just won't work. In the labs or the ARM processor that we're working with, we worked with a little endian configuration. And remember what I said before about little endian was that meant that the lowest byte, for example, the 9.1, got stored at the lowest memory address. So for this question here, where we have a particular number and we want to store it in both little endian and big endian configurations, let's see how that actually looks. So for little endian, we take the lowest byte and we chuck it in the lowest memory address. So that corresponds to the 40000 here. So that's going to be 0x91. And then we just keep going, right? So we just get the 84, that's going to go in the next lowest one. So 84 here. Then we're going to go with the 52. So the 52 will go here. And then finally 0 is going to be at the bottom. Well, big endian is just the opposite of little endian, in that the lowest byte of your number gets stored at the largest memory address. And so it's really just the opposite. So it looks somewhat like this. And 0 over here. So important distinction, but yeah, little endian, I remember by just saying that the lowest byte goes to the lowest memory address. Okie dokie. All right, how are we doing for time? We're doing pretty good. Okay, so let's talk a little bit about control flow now, and yeah, that sort of thing. So the question is, like, how do we update the CPSR flags? There's 3 different ways that you can do it. And remember one of them? Yeah. So compare, etc. So that's going to be these 4, which we'll talk about in a moment about what they actually do. So yes, there's comparisons. Any other thoughts? Yep. So if I do like an add, like append S. So if I do something like add S, R0, R0, R1, that will update the status flags based on the addition. Last one. That's the tricky one. Okay, you could manually change them. Sure. No. I'm talking about updating them based on an instruction. Yeah, but it's a good point. The last one is that when you have a shift, so if you have a shift on something, for example, like something like this. I actually need an S here. Because the OR the OR doesn't, doing a logical OR doesn't end up with a carry flag, right? You can set perhaps the negative and the 0 flags. That makes sense based on the result. But because there's no additional subtraction, there's no carry flag, so the C flag doesn't get updated. You can update the C flag by adding a shift, something like this. And what that will do is it will basically update the carry flag with the last bit that gets shifted out. So a shift to the right, you guys, it's going to be going that way. And so a shift to the right is just going to be the last one that gets shifted out of your particular register, because you're going to lose bits off the end, right? So shifts update the carry flag with the last bit shifted out. Cool. And we can put an example here as well. Okay, so they're the 3 ways that we can update the flags. Let's just talk about exactly, looking at the first one, the comparisons, exactly how they work. Compare is really easy. We used to use this in the labs quite a lot. It's very logical. What does it actually do? It actually performs a subtraction. So it's basically the same as a like a sub S with no destination register. So because like the comparison, we'll do a subtraction, it just doesn't store the result anywhere, but it updates the flags based on that subtraction. So that's always nice to think about that way, because that means if we compare 2 numbers to each other, and what we want is we want to see if they're equal, we do a subtraction, and if we get 0, then the numbers are equal. So that's always nice to kind of look at that how it works from that perspective. Okay, so if compare does a subtraction, what do we think compare negative does? Addition, yeah, nice. Same as an add-s, really. So same as compare, but just does the negative, so it's same as an add-s. Okay, test and test equal a little bit more estranged. So test does a logical and on the 2 things. So you'll do an and of the 2 arguments. So it's really like an and s, in all honesty. And then test equal is a bit of a weird one, but it does a logical XOR of both of the 2 arguments. So that's what those 4 things do in terms of like the actual values involved. And they will set the flags based on the result of that. Cool. How long have we got to go? All right, we might just finish these last little bits and have a break before we talk about functions and interrupts. Cool. All right, how long does it take a branch and link instruction to execute? Hopefully we all know this. Oh, you have a question? So test does an and, test equal does an exclusive or. As to what that actually means, if we think about what the exclusive or, it's a shame that not very likely. It's a shame that that's kind of gone. Maybe I can quickly give me a second to get this up again, because it's just going to be easier. Oh. One, two, three. So if we're going to do like an XOR of 2 things, it's actually an interesting question. If I take the XOR of 2 things and they're exactly the same, then the XOR of these guys is going to be what? 0. So XOR is used to test if two things are equal. So if I was going to going back to 2-on-4-on-5s, if I was going to go and write hardware or make hardware, design hardware that tests if two things are equal, this is going to be a lot simpler than doing a subtraction, right? So this is kind of, I guess, why it's there. I mean, you can also probably do it with compare, but this is just a nice way of thinking about it. For test, what does an AND do? It's a good question. Let's have a look at the same example. If we were to do a logical AND of these ones, we get the same thing. I can't remember off the top of my head exactly what the test is used for, but there'd be a specific use case similar to the test equal with the exclusive OR, where it would be used for something. Testing equal to 0. I remember. Oh yeah, possibly. So if we wanted to test whether a particular bit was equal to 0, we could look at, for example, we had a mask 0, 0, 1, 0, and then we did the logical AND of these two, which is the what is it, the test PST thing. Then that would be something that's not 0, so we get 0, 0, 1, 0, right? Which is not equal to 0. And so we would be able to tell whether or not that bit is set based on that. So I think it's just testing whether a particular bit is set.
I think from the instruction set, they've been mentioning something about equivalent test, bitwise test, logical equivalence and bitwise.
Right. Okay.
For the test of T, sure.
Yeah, not too sure.
Building up some realistic relationship. Like the arithmetic compared.
Yeah, I have to have a look at the manual to see exactly what you're talking about there. But I think as a method of just testing whether a single bit is set, this is kind of nice. But we can see it's exactly equivalent to the Endianness function anyway. Okay, so a bit of a sidetrack, that's okay. So back to branch and link. So how long does it take? 3 instructions, right? Why does it take 3 instructions? Because as well as the fetch, decode, execute cycle, we also have 2 other stages, which are the linkret and the adjust. So what do these actually do? So linkret actually does move LR BC, and the adjust goes and does sub LR hash 4. Apologies, sorry, I'm back. Yeah, so just before my computer crashed, we were talking about the branch and link instruction, and we decided it took 3 cycles to execute. That's because of these 2 things here, the linkret and the adjust. So the branch and link goes through fetch, decode, execute, and then it goes through linkret and adjust, which is all just making sure that the link register has the right value in it. And so it'll do sub 4 from the link register. Cool. That's just more of a memory jog. Hopefully that's embedded after the labs. But something that's not particularly explored in the course anymore, but I still want to cover it as an interesting example, and it's good for analysis of code, is the concept of how loop unrolling works. So I don't think you're expected to know what loop unrolling is, but it's interesting to just look at the benefits of it anyway. So for loop unrolling, we have this loop here, and the idea of loop unrolling is that you kind of make it operate faster. Now, how do we do this? We should first just work out exactly how many cycles it takes to execute this block of code. So if we just add everything up, we've got 2 at the beginning that execute once. So I'm going to do 2 multiplied by 1, plus we've got 1, 2, 3. Remember the branch takes 3 in cycles, so 4, 5, 6. So 6 cycles times the number of times this loop runs. So what is actually happening in this loop? We've got R0 with 10 at the start, R1 with 0, and we keep adding 1 to R1 until we get to, whoops, I think that should be a 10. There. Oh no, compare R0. Sorry, we keep adding 1 to R1 and we keep subtracting 1 from R0 until R0 gets to 0. So R0 starts at 10 and we just count down until R0 gets to 0. So this loop will happen 10 times. So in terms of how many clock cycles, it's just going to be something like this, which is 2 plus 60, which equals 62 cycles for this particular code. With loop unrolling, what we do, let's just copy and paste it down here, is we kind of take 2 iterations of the loop and we place them one after the other so that we only have 1 branch instead of 2. So what it would look like is it would look like something like this. And because of that, so we can kind of get rid of this one. Well, actually, if we were going to be complete, we would have to say branch if equals to stop. So I've kind of got 2 iterations of the loop here in 1 iteration of the loop. And the reason I can do that is because, well, rather than just starting from the top again, I just duplicate the contents of the loop. The only thing that needs to change is this branch in the middle. Rather than branching back to the top, we just want to check whether we need to stop. And if we need to stop, then we go down here. So because of that, I check if R0 is equal to 0. And if it is, then I'm going to branch to the stop condition. So that's what our code would look like if we do loop unrolling. And now let's have a look at like the complexity of this code. So we have, again, we've got the 2 instructions at the beginning. But now what have we got in the loop? 1, 2, 3, 4, because this is pretty much never going to get executed as a branch. 5, 6, 7, 8, 9, 10. So it's like 10. But the entire loop gets executed 5 times instead of 10 times now. So we have a 5 here. And so that gives us a total number of 52 cycles. So we can see that by doing this loop unrolling, we've got 2 iterations of the loop in 1 iteration, and that saves us 1 branch, right? And on the whole, we can see that 52 versus 62 is actually a pretty decent improvement for 1 level of loop unrolling.
We tend to apply something.
Sorry.
When we take up like 3,
Well, like when we think about it, like 10 is an even number, right? So when it breaks out, it's then going to break out there. It's going to break out here. Okay, yes, sure. It's going to take away 2. Yeah, it will take away 2 the last time because the branch, sure. I get what you're saying. So that last branch, the last time it gets executed, it will not branch. It'll just fall through into the stop. So because of that, this last branch will only take 1 clock cycle to execute. So really, I should have done -2 here to give 50. And again, I should also do -2 here to give 60. So yeah, just because that last branch, the last time it gets executed, when R0 is equal to 0, it will only cost 1 cycle because it will just fall through. You don't branch. Yep, so sure, good catch. But yes, in terms of how much each instruction costs, remember your branch costs 3. Your data processing usually costs 1. And load and stores are usually 3 as well, but it should be defined in the question that you're doing in the exam. That's how it has been in past papers anyways. Okay. So moving on to functions and subroutines. So we've covered this in the labs quite a bit, but it is important to know so that if you get to the exam and you have to write a routine, that you know exactly what registers you are using. So in terms of the responsibilities and rights of both the caller and the callee, I think first we should just define exactly what the caller and the callee is. So if we have a look at an example, if I have my main function looking something like this, and I call a function foo, then main would be the caller and foo would be the callee, right? So in terms of the actual call, this is what I refer to as the caller, or in this case main, and the callee would be the function that you are actually calling. So in terms of what they should do and what they should expect, these are their rights and responsibilities, right? So the caller, in this case, our main function, has a responsibility to do a couple of things. The first thing that it needs to do is if it wants to use A1 to A4 after the function call that it's going to call, it needs to save them. So it needs to save A1 to A4 if it wants to use them afterwards with those values. Because remember that the callee can modify A1 to A4, right? The other thing it needs to do is it then needs to set up the arguments for the function. So that will include A1 to A4. So really, this should kind of, the setting up arguments bit logically comes before saving them. And so you set up the arguments, and if you need to use those argument values after, then you need to save them. So we set up the arguments, and that includes putting them on the stack, right? So remember that the first four arguments go in A1 to A4, and then everything past that goes on the stack. And we'll have a look at an example of this in a second. Cool, and it saves A1 to A4. The rights of the caller is that it expects that V1 to V8 are unchanged. So it means that the function has not changed V1 to V8. The function can use them, but it needs to save them first. The other thing that it expects is it expects a return in R0 or A1. So those are the rights and responsibilities of the caller. In terms of the callee, corresponding to like this sort of thing, the caller expects V1 to V8 unchanged. So if the callee wants to use them, it needs to save V1 to V8. Cool. It also has a responsibility to set up the return in R0. Cool. The only thing that the callee has a right to then is that it can expect the arguments in A1 to A4 and then on the stack. Cool. So hopefully that all makes sense. If not, let me know. Because now we're going to have a look at a question where we have a function P calling a function Q, and we want to look at the stack frames for P and Q, considering the information there. So I'll just jump across to the whiteboard so that everyone can see what's going on. Cool. So here's our question. Before we talk about exactly how to answer this, it's probably a good idea to talk about what stack frames are, because that might not be a term that you're familiar with. And then basically in terms of how your memory works, so that we have an idea of what happens. So you might remember from the lectures that your memory is basically one giant array, and it has different sections, right? Right down the bottom, it's got your code, and then above that, it's got the data, so all like the hard-coded constants and strings. And then over here, you've got your static, which is basically all your global variables. And then finally, you have the heap, up here, and you have the stack at the very top, and the heap and the stack grow towards each other. Now, the stack for us is definable. Remember, we have 4 types of stacks. We have 2 options for descending, empty descending or full descending, and 2 options for ascending, empty ascending and full ascending. But I'm going to assume here that we're using like a full descending stack. But once we get to the question, we'll be talking about an empty descending stack. But we'll get to that in a second. Well, let's just say that we're going to assume a descending stack. We won't say whether it's full or empty. So the stack and the heap grows towards each other. Cool. The heap is used for malloc and that sort of things. So you won't usually use it in your assembly code. But stack over here is used quite a lot, as we've seen in the labs. So what is a stack frame? Well, perhaps I just need to move this. Yeah. Okay. Oh no, it doesn't really matter. So if we redraw our memory, and we have our stack, the stack is used for variables and stuff related to functions. So if we have a main function that calls, our function foo, on the stack we'll have main at the top, and then it will have a stack frame for foo underneath. So a stack frame is basically just all the data associated with the function foo. What data is associated with the function foo? Usually just all the local variables in that particular function. So foo is defined as a function here, and we have an int I, then int I would live up there. Cool. There's also a whole bunch of other stuff to do with the arguments on the stack and saving registers, and they will correspond to the particular frame for that function. So if we jump back over to the actual question here, we can talk about exactly what this question is asking. So where we got P calls Q, and we want to draw the stack frames for P and Q given the following information. So the first one is that it has an empty descending stack, which is different to what we've usually been using. And what that means, remember, is that in terms of a stack, the stack pointer basically points to the first empty spot on the stack, as opposed to in the labs we've been using a full descending, and so it will point to the first full, but we're going to be using an empty descending stack. Cool. P has to pass 7 arguments to Q, and P uses registers A2, A3, B1, B2 after calling Q. Okay, so let's draw up our stack, and let's have a go at drawing up exactly what the stack frame actually looks like. So for P is going to be what we do first. So I might do P in green. P passes 7 arguments to Q, but it also uses A2, A3, B1, and B2. So we've got 4 arguments that P, which is the calling function, is using after the call to Q. Which ones of these do we need to save before we go to the function? Yeah, nice. So we don't care about V1 and V2 because it's implicit that the function that you call will save those if it needs to use them. So the first thing we're going to do is we're going to save the registers appropriate. I should probably start by saying that the very first thing that needs to be saved here is the link register, because we're about to call another function, so we need to make sure that we maintain the link register. And that should be like probably done at the very start of the function P, but I'm just going to put it there for completeness. The next thing, A2 and A3, we need to save them before we actually set up the arguments on the stack. So A2 and A3 go on first. So they will go in this particular order: A3, and A2. And the reason we have it in this particular order and not the other way around, for example, not like A2, A3, is because when popping it off the stack after the function call, we want it to be in the appropriate order in terms of the registers. So if you use, for example, a load multiple instruction, it will save it in this format. Cool. All right, so we've saved the registers that we need in P. Now let's set up the stack in terms of the arguments for Q. So remember that P has to pass like 7 arguments to Q. I'm going to call them like arg1 through to, arg7. And so the first 4 arguments, arg1 to arg4, are going to go in A1 to A4, so we don't need to pass them on the stack. But the next 3 do need to go on the stack. And again, it's similar to this convention here, where we would put the lowest argument at the bottom of the stack. So what's going to happen here is we're going to have arg7 followed by arg6 followed by arg5. So that's what our stack looks like. And this is the stack frame P. Cool. Any questions about how we set up the stack frame for P? We haven't talked about Q yet. Yep. So the idea is that the stack pointer was empty descending, so it's going to point to here, right? So when your calling function goes to access the arguments, it kind of makes logical sense that the first argument it gets should be argument 5, right? Not argument 7. It'd be just a little weird to go argument 7. Anyway, it's just how it works in terms of.
8, 7 to or 7 to R5.
Sure, but you'd be breaking the AA PCS, right? So this is how it works for AA PCS. If you want to define your own standard that does the other way around, that would be fine, but you need to be consistent, as in you'd have to address both the calling and the call side. You'd have to personally write both of those. You couldn't write a C function because the C function is going to assume that something like this happens. Does that make sense? Yeah.
So suppose we use, in this case, we use empty assignment for pushing on the register to the stack.
Yeah.
Is it kind of safe to assume that when the function is popping out popping out from the stack, it also uses the empty the other way around?
As in, like, it should use the same stack sort of format. Sorry?
The order.
As in, like, it won't do like a full descending sort of thing. Is that what you're saying?
Is it the other way around? But it's
When it pops off, yeah, the stack pointer will move up. Yeah. It's a good question actually, because it is going to read these arguments from the stack. But I think the important thing to remember about the stack is that you really don't touch the stack unless you don't modify the stack unless it's part of something that you modified earlier in that same routine or function. So that means that P is going to be the person to take these ones off the stack. Q, the function that it calls, just reads them. It doesn't actually modify the stack pointer. So it's always, if you put something on the stack, it's that function's responsibility to take it off. Now, because P put those arguments on the stack, P takes them off. Does that make sense?
But if they change the way such that, for example, it's full ascending when it pops off,
Yeah.
then it's gonna kind of change the position for where the stack pointer is pointing at the next available.
Yeah. So everyone needs to use the same stack, because then everyone needs to use empty descending, or everyone needs to use full descending. If you start mixing them, they'll be, of course, like you're going to, it's not going to work, right? Yeah. Yeah. So you need to make sure that's consistent as well. Cool. Okay. So the second half of the question is we've got to talk about the stack frame for Q. So Q uses registers A1 to A4 and V1 to V3. Now remember that Q can use A1 to A4 without having to save them, but it does need to save V1 to V3 in order to have this work. So I'm going to draw this stuff in red now for Q. So what it'll do, again, it's going to go like V3 B2, B1. And now this makes up the stack frame for Q. And then of course, at the end of the day, let's get rid of the cool. At the end of the day, the stack pointer is going to point to the first empty slot after V1. Okay. Does anyone have any questions about that? In terms of when Q returns, the idea is that Q needs to clean up everything it did on the stack. So that means that after Q returns, it should move the stack pointer up to here. So that basically P sees no change in the stack pointer. And then what P is going to do is it's going to, well, it doesn't really care about these ones. It just kind of jumps up and then it will take A2, A3, and probably not the link register because it'll do the link register at the very end. But it'll take those off. Okay.
Is SP automatically updated when you?
No, it's similar to like the pre-index stuff. You need to put like an exclamation mark. So in terms of like your load multiple, you would need to specify like the type of stack. For example, we're using a empty ascending stack. So load multiple empty ascending stack pointer exclamation mark. From memory, I'm pretty sure. And then yeah, sorry, that's not the right bracket, is it? The list of registers that you want. Yeah.
Store multiple.
Yeah, so store multiple, like this is what makes it really easy. If you just keep using EA as your thing, you don't have to worry about specifying exactly whether it's, increment after, decrement before sort of thing. And it's the same vibe. Yeah. So you're just going to make sure that whenever you write a function that you match your loads and stores with the stack pointer so that the stack pointer is the same as when you entered the function. Cool. All right. Any questions about this one then in terms of how stack frames work? If it's empty, sorry, I should have said empty descending. Because sorry, for this one for load, because we're loading from the stack pointer will go up. And so what that looks like is that it's going to be incrementing and it's going to increment before because it points to an empty slot, right? So you want to increment before and then load. So that would be the equivalent of IB. And then this one for the store, you would want to decrement after. Make sense?
So the assembler will sort of.
Yeah, I can't remember whether it's the preprocessor or the assembler, or whether that just happens, whether you can just say that and it works it out. But yes, as in I can't remember whether that's a pseudo instruction or not, and whether it gets translated to a STMDA, but it works it out somewhere along the pipeline. Yeah.
So IDA, you're like using it for non-stack purposes.
Yeah, I mean, like if you have like an array, it probably makes sense just to use one of those things because you just need to load from it. You don't need to store from it or something. Yeah, if you use a stack one, it's just nicer so you don't make any mistakes, right? So because if you screw up your stack in one of your functions, then it's gonna be a very hard error to find. So if you just make it really simple for yourself by using the same thing, it just makes it easier. But it's totally up to you. You can mix and match how you want. I think you had a question.
What do we do with like our supply for stepping up? Finish, we just like increment the stack pointer.
So P needs to increment the stack pointer. Yeah. Yeah.
You just like,
so we only do it. There's nothing I can think of unless for some reason you wanted to use them in P, but I can't think of a reason why you'd want that because they would probably be in V1 to V8 anyway. Yeah. So P just needs to increment the stack pointer up to A2 and then load A2 and A3 back. Yeah.
So in a piece of code that's saying between the assembly, if the quarter is C, does the programmer need to manually save these arguments for the compiler to
So if the caller was C, so if P was in C, then P would do all the green stuff. And then if this was in assembly, you would have to do the red stuff. So it's very much that whenever P sets up, P cleans up. And so if P sets this all up, the C code does it for you as part of the AA PCS. So you can assume that basically on entry to your routine, the stack looks like that with like all the green stuff.
So the programmer doesn't have to set up this stuff and instead the compiler will.
Yeah, if you write it in C, the compiler does that for you because it sets up the function call like that. Yeah.
How would you access the arguments that P has?
So they're on the stack, right? So when we enter the Q function, the stack pointer is here, right? Because P set this all up and the stack pointer is here. So to access then you would just be like, well, you can't do this because you don't want to modify the stack pointer, but you can do it without the exclamation mark. So, but if we wanted to just talk about like, you could just do a simple PC offset. So LDR R0 stack pointer hash 4 argument 5, right? And that way we don't update the stack pointer. And so the next one would be like a hash 8 in order to get argument 6, then hash 12 to get argument 7.
So you can do that for pushing the P.
No, well, I'm loading the R0, right? So I can do whatever I want in R0.
Okay. But let's say you had 5 arguments passed in, so
Yeah.
that's not enough.
So then I would need to put V1 to V3 on the stack first.
And then do it manually by putting it back.
So the stack point is now down here. So the offset to argument 5 is going to be 1, 2, 3, 4 instructions. 4 times 4 bytes is 16. So your offset is going to be 16. Right. So you just got to do a little bit of manual calculation there as to how many arguments you're pushing onto the stack there and how much you need to increment by to get to what you need. Make sense? Yeah. Okay. So Katrina, just to double check, if it was ascending, we'd still have V2 higher than V3. That's a good question. I believe so, but I would have to double check on that one because I've only worked with like the full ascending stack in the labs. And you can go and actually see this in the registers or in the actual stack. I would assume so, but I'm not too sure.
It's always the lowest range. It's the lowest range.
Right. Okay. Because it's done by load the LDM. Yeah. So yeah. Yes. So V2 would still be at a lower address than V3. And so yeah, the reason that Jack just said, if you didn't hear that, not sure how good the microphone is that that's how LDM and STM work. So that what is this? Because that's how LDM and STM work. We want to make sure that we're compatible with LDM and STM. And so because LDM and STM always store V2 below V3 or V2 at the lower memory address, that's how the AA PCS works. Cool. Okay. That was a lot of talking. We should talk about IO interfacing. We should probably spend some more time on this part. So very quickly, we go through IO interfacing because we've done a lot of this in the labs already. So what is memory mapped IO? It's basically when you have registers for your memory. So if you remember, we just wrote to like the pin register or the set or the clear. Well, the pin register is really the memory mapped IO. And so because we wrote to a register and that was connected directly to the actual LED, that is what memory mapped IO is. So you can think about the LED actually being kind of directly connected to a bit in that register. So to type that out, memory like a register is used to control IO. Cool. So then what's the difference between polling and interrupt driven IO? So remember that like polling is where we're constantly waiting for something to happen. So you might remember in the sound lab when you're waiting for the timer to match with the match register. That's pretty much polling. So you're just in a loop, constantly checking something. And the difference between that and interrupt driven is that with interrupt driven, we don't need to keep checking something. We just run our code and the interrupt just basically stops our execution at a point, and we jump to an appropriate handler that handles the interrupt. And then we go back to the middle of our code wherever we were before and we keep going. So interrupts are much nicer because we don't need to hang in a loop. So we can just set up, for example, the timer and go away and do something else. And the processor will interrupt us when that timer has matched. And so interrupt-driven I/O is a lot more efficient and lets us do multiple things at once, whereas polling, you don't really have the opportunity to do multiple things at once. Does that make sense? Cool. I'll type out a appropriate answer later. It's just going to take me a while. Okay, this is what I really want to talk about, so that you have a good understanding of these things before the exam. So constant pseudo instructions and literal pools. Okay, so this is all to do with basically loading constants into registers and doing stuff with them and the limitations of the instructions around that. So the first question, what are the limitations of move? So, I mean, move is of the form, you know, some destination register, and I'm talking about when we have an immediate. Cool. So with move, we have this sort of format here. What that looks like in terms of an instruction, remember that all of your instructions are 32 bits, right? So, we start a new one. Your instructions are like some 32-bit value. So I'll write 0 to 31. So you only have this amount of space to actually have the instruction in. So by the time you account for the facts like conditions, which is where like if we have a move, we add like equal to it. So that condition is basically stored here at the start. And then you've got more or less your opcode, which is it a move, is it a branch, is it a load, is it a store? You know, what instruction is it? And then you have your destination register. By the time you've finished having all this stuff in your instruction, there's not a whole lot of space to have a constant. So remembering that like for move, we have for a destination register, we have an immediate. The space for the immediate actually only ends up being 8 bits, which I should represent by having a 7. A 7 there. So there's only actually 8 bits for that immediate, which is, well, it works for us because usually we just want to move like a 0 in or like a smaller number. But sometimes we want to generate like a larger constant. So we can see that there's a limitation on how move works in that there's only 8 bits that can be used for the immediate. There is a bit of a interesting thing with move though, in that you can add a rotate right value to it. So you can also do a rotation to the value. So in terms of what the immediate looks like, the immediate is somewhere between like 0 to 0xFF, right? With the rotate right, we can take one of these values and we can rotate it right. There's a little bit of a catch here in that the rotation has to be basically a multiple of 2. So the rotation has to be, it can't be odd. And so you can imagine that we can now generate numbers like, for example, 0, 0, F, F, 0, 0, 0, 0, because we just take FF as our immediate, and then we just rotate it right so that the FF sits here instead. So that's just an important one to remember. Basically, anything you can generate with an 8-bit immediate and a rotate right, move is used for. The reason I'm talking about these sorts of things is when you go and load a constant in, and we'll talk about this in a second, if it can use move, it will go and use move. Like the compiler will translate that to a move. All right, so if we're happy with how the move function, the move instruction works and its kind of restrictions, then move negative is the next one that we need to talk about. So move negative is also very similar. in structure, and that we only have an 8-bit immediate, but we also have the rotation again. And so move negative basically takes your 8-bit immediate, which again is in the range 0 to 100, 256 or 255. It will negate that first to give us something like lots of F's. One more, for example. So it negates first, and then it goes and does the rotation. So you can think of move negative as generating the complement of everything that you're able to generate with move. So this allows you to generate some larger numbers, but not huge numbers. So it will allow us to generate stuff like this or FFFFFFFFF. Cool. So move negative works in that way. All right. And so with the, well, let's just go down here. So we can generate those sorts of numbers, but as you can imagine, there's like a whole range of numbers that don't fit the move and move negative. So how do we end up doing those ones? For example, if you remember loading like the addresses for the FiO3 pin, FiO3 clear, they're all huge numbers and they weren't going to fit move or move negative. So how do we go and do that? Well, you would use something like, let's write it over here. Equals whatever number that you wanted. For example, we were to choose some random number. This is how you would have done it in the lab, or you would have replaced this with an EQU and just typed FiO3 data or something. But yes, so this is how you would do it. This is a pseudo instruction. It's not an actual instruction. So how does it actually get translated to something? Well, your compiler will first look at whether or not it can do this with a move or a move negative. And if it can do it, it'll just replace it with a move or a move negative. If, like this scenario, you cannot replace this with a move or a move negative, it's going to go ahead and place the constant in a literal pool and then load it with a PC offset. So I imagine that probably most of you are not very familiar with what a literal pool is and how it works. So let's talk about that for a second. When you have your code, at the end of your code section, you will have what's called a literal pool. And so this is where all the constants get stored. You can probably remember from the labs, we used to have like a DCD or something, but it was right at the bottom underneath all your code, so that it wouldn't screw with the execution and the actual instructions. So what we would do then is that the compiler would take this number, it would place it in the literal pool, and it would replace this with a PC offset. So it would be LDR R0 PC and some sort of offset. And in terms of what that looks like, remember I kind of said that your code was down here, right? So then you've got your literal pool like kind of next to your code. So this is all well and good, except can anyone remember what a limitation of LDR is? Kind of similar to what we talked about with move and move negative. The offset. Yeah. How many bits for the offset? Remember? No? 12. So we have 12 bits for the offset, but you can imagine that only really takes us to 2 to the 12 is 4096. You actually get plus or minus 4095 because in the LDR instruction, which again looks something like this, there's a sign bit in there to tell you whether to go plus or minus. So you get plus or minus 4095. So if I have this constant right down the bottom of my code section, and my code section is like 10 kilobytes, like 4095 isn't going to cut it anymore. And so there has to be a way around this. In fact, in this particular instance, the compiler will just fail and it will tell you that it can't compile because the offset is out of range. This is where we have to come in and we say, okay, the literal pool that was automatically created here is not close enough to the code that needs it, right? So what we do then is we would explicitly place a literal pool somewhere in the middle of our code that is within the 4095 byte range. What that looks like is if we have some sort of code, we would just use the assembler directive LTORG in order to place a literal pool at that point in the code. Now that comes with inherent danger, right? If I have like some code here, I could just accidentally start executing stuff in the literal pool. So you just make sure that when you do this, that you put an unconditional branch to wherever you need to be afterwards. You can do it like this, or you can place the literal pool at the end of a routine where you know it's never going to get executed because there's an unconditional branch above it, but you need to have something like this. And if we place this literal pool somewhere within 4 kilobytes of the instruction that needs to access it, then the compiler becomes happy and we can go forth and have fun. Does that make sense as to how the literal pool works? Yeah, roughly every 4 kilobytes or something. Yeah, 8 kilobytes really, because it can go plus or minus. But yeah, you just need to make sure it has access to that. Of course, that's only if you need to load in a constant that's that big, right? And you can imagine that writing code that's that large is, probably not very common. So we won't get there with our labs.
Offset for the small.
Yep.
Does the literal pool get created in that data section of the
I'm actually not entirely sure. I'm pretty sure I was reading about how the linker puts everything together earlier, but I think my guess is that it goes at the end of the entire code section, sort of like in between the code and the data section. But that's just my guess. I'd have to look up to let you know. Yeah. You don't need to know that for the exam. Cool. Any other questions? So just remember those limitations around move negative, and load for the exam. Cool. So there's no questions about. There's a couple of questions in terms of what are these ones translated to. So the first one, we're loading a 0x2142. Now, this can't be generated with a move or a move negative because the constant is more than 8 bits long, right? And so it just doesn't work. So this one would be like an LDR with a PC and an offset, which we have no idea what that would be. It would just be what the compiler kind of generates. Okay, and then we go for 42000. We can see that 42 by itself is 8 bits long. So we can achieve that with 8 bits in a rotation. So this would just be a move. And then the last one, again, this is kind of the opposite. We've got like some zeros at the beginning. So we just do a move negative. So there's only, because everything else is 1 apart from the 8 bits of zeros, then we just use a move negative instead. Okay. Exceptions and interrupts. This is kind of hard for the exam because it's difficult to come up with a coding question for exceptions and interrupts, given that you haven't done it in the labs or anything. So although I'll cover it theoretically here, yeah, I'm not sure how thoroughly this will be tested in the exam, but that's just my analysis. Exceptions and interrupts. So we have a number of exception sources in the processor. Can anyone tell me what some of them might be? Where might we get an exception from? So the first one might be reset. So if we hit the reset button on the processor, that's an exception to the processor. It will stop it. The reset's an interesting one because it's the only exception that will interrupt you mid-instruction. Every other exception will allow the processor to complete the current instruction. Reset doesn't, just go straight back to 0. Cool. Other ones, undefined. So we talked about the undefined mode before. So if we have an undefined instruction, we generate an interrupt that will take us to the undefined instruction handler. Cool. Software interrupts. Software interrupt is something that you can place in your code, and it's like a pre-planned interrupt. So you can interrupt your own code at that point. So it's interesting in where you use it. We used to do it in one of the later labs, but we don't do it anymore. But yes, it's just another form of interrupt that you can use to interrupt your own code. Prefetch. Sorry. Yeah, so I think the SWIs can be used as for debugging processes. So for example, if your SWI handler was, so if you were testing your code on OS, you could jump to your SWI handler and perhaps do like a print statement. So you could print back to the containing OS that can tell you what your processor is doing. So your software interrupt can be used for debugging purposes in that way. Yeah, that's nice. Yeah. Cool. Prefetch abort. So this is when the processor attempts to execute an instruction that was not fetched because the address was illegal. For example, if you try to load an instruction from the data section, the processor's like, hey, that's not an instruction, so you're not allowed to do that. And it gives you a prefetch abort there. Cool. Data abort. If you try to load a value from address 0, you're going to get a data abort because trying to load from 0, you're loading an instruction, anything in that small 0 to like within the code section, roughly, or the first section that's defined for like reset handlers and that sort of thing. If you try to load from there, the processor says, hey, you're not supposed to. And this is exactly the same as a segmentation fault in C. If you try to dereference a null pointer or load data from address 0, it gives you a segmentation fault. This is just the processor equivalent of that. So data abort when you try to read data from memory that you shouldn't be reading from. Okay, the last two are IRQ and FIQ. We sort of talked about them before. So IRQs are just interrupts in general, and then FIQs are fast interrupts. So they're ones that get priority. So in terms of priority, like reset has top priority, and then FIQs are more important than the IRQs. And so an FIQ can interrupt an IRQ, but an IRQ can't interrupt an FRQ, and so on and so forth. Cool. So why is FIQ faster than IRQ? If it's fast interrupt, how do we actually achieve this? There's a couple of different things. Most of the modes that we define at the beginning have their own set of registers, but how many of those registers it has depends on the mode. Most of them will have their own program status register because they just need that. But as to the general purpose registers, usually they don't really get a whole lot of them. The FIQ mode does get like 6 or 7 extra registers. So it means that the FIQ doesn't have to go and save everything. It just has a separate bank of its own registers. It just goes and uses them. So it has its own set of registers that it just goes and uses. So it doesn't have to save everything. A second example of how fast it is where the exception handler is. So when the exception occurs, you can think about these as being addresses, one after the other. Reset at address 0, undefined at address 4, 8, 12, 16. So each handler, each kind of entry point for the exception has an instruction worth of space at the very beginning of memory allocated to it. That is usually a branch to the actual handler for that exception. So for example, for undefined instruction, there'll be a branch to a section called undefined instruction, and you can write code there to deal with undefined instruction. This is where you can say, hang on, the instruction looked like this, and this is where you can define your own instruction, how it works. But anyways, so the FIQ is at the very bottom of this vector table, and as a result, that means that it doesn't have to just jump somewhere. The handler is just right there. So because it just starts executing the handler, there's no jump or branch involved, and so it can just keep going. So so FIQ is last in the vector table. Is another reason why it's super fast. It's also higher priority, as we discussed before, and we generally only have one FIQ. If we have more than one FIQ, that defeats the purpose, right? Because that'll be queuing, and then yeah. So we generally prefer to only have one FIQ, and the rest be IRQs. I might fill that out later. It's just copy paste from your lecture slides. Okay. processor. Yeah. So you don't want to have an FIQ hooked up to your keyboard, right? Because your keyboard is not very important. Like, yes, it needs to eventually get serviced, but like if you miss a keystroke, like nobody dies. Whereas if you had an FIQ on, for example, like, the nuclear bomb is about to explode, that's probably more important. So you can kind of classify your risks and the interrupts and choose the most important one for that situation, the one that you need to handle promptly.
Is that something that would be the program, or is that something?
So your FIQ is just like an input to your processor, like it's just a wire, right? And so you can choose what you connect to it. How you handle it is all part of what you write. So remember I said that the handler for the FIQ is just a bunch of code that starts from this entry in the vector table. So you would write that code based on what you want to do when that interrupt actually happens. Does that make sense?
Yes, or like a application that you might write. Something.
Yeah.
So when you're saying like one FIQ per microcontroller,
Yeah, usually, yeah.
is that like, I mean, it's a bit weird for a microcontroller, but is that one FIQ per core, or is just control?
Look, I'm not entirely sure how these concepts relate to multiple core processors, but you would usually only have one fast interrupt, and the reason being that like your regular interrupts are going to get serviced fairly quickly anyway. It's just for situations of quite literal life and death. So a fast interrupt for a processor for a PC might be like the power is, been unplugged. And so the processor literally has probably 20 cycles to save its state or something, like, so it's going to use those 20 cycles to, like, it wants to just it doesn't want to wait. It just wants to do that. I can't think of anything more important for like a PC, for example. Everything else can wait, a couple of microseconds. Whereas, if you turn the power off, like the PC probably wants to save some sort of state before it crashes and burns, right? As for multi-cores, hit the Google on that one. I'm not too sure. Yeah. Okay, cool. So I have a more involved example, but we might quickly talk through this before we finish up. So for this example, we've got some C code, and the questions are about the C code in terms of what does it do, what does it output, and let's write it in ARM. So take a minute to just read the code, and then we'll talk about what it's actually doing. Sorry. No, I think that's just how it's supposed to be. Yeah. Which is good. So ask that question. If you're not sure what the syntax is, that's probably a good opportunity for us to talk about it. Yeah, cool. So have you had a brief read? Are there any lines of code that don't make sense and you're not sure what they're doing? So I can explain them to you now. Or otherwise, I'm going to assume that you know everything about the if statement. So if star A is equal to C. All right. So what are we doing on this line of code? So particular condition. What is A? A is just a pointer. Right? A holds a memory address to a string. What that really means is A holds a memory address of the first character in that string. So from our point of view, A is not actually a string. A is just a memory address. How long is the string? We just keep iterating from that memory address until we get to a null character, the 0 at the end of the string. So if A is a pointer, then what does star A do? It dereferences the pointer. So it grabs the memory associated with that memory address. So we know that A is pointed to a character, so it's going to go and grab the character that A points to, which is going to be in the first instance the T there in B. Now we're going to compare it to C, where C is defined as a character O, right? And so we're comparing a character to a character, so it makes sense. Cool. Any more questions about the code, or are we all over it? Cool. Yeah. Yes. Interestingly, it will increment by whatever the type is. So if it was an array of integers and you do plus plus, it will add 4. But yes, in this case, we're just going to add 1 because we're pointing to an array of characters and the character's 1 byte. Cool. So what does it do? Anyone have a stab at what the code's doing?
That's the characters on the right side of the screen.
Yeah, and so it will just print out basically the remainder of the string starting from the last O. So if we were to run this, it would print out. So what is the output? It's going to basically print out, yeah, UGH. I just type UGH. Yeah, just like that. So that's all the code is doing. Okay. Do you want me to go through? I know we're over time now. Do you guys want to hang around while I do part 3, or do you want me to just copy paste and you can look at it later? It's probably the more interesting part, but it's up to you guys. So part 3 is literally writing that all in ARM. So I'm super happy to, but if you guys want to head, that's also cool. Thanks. Yeah, it will also print the O. Can we do part 3? Hands up if you want to stick around for part 3. One person? No, cool. That's all right. I might just do it anyway, and if you guys want to head, you can head. Yeah, sorry, we ran out of time to get to the Kahoot, but you guys have the link, so I'll post this document. You have the link to the Kahoot if you want to do some practice later. The only thing is, if you want to just leave me some feedback on what you thought was useful, what you thought wasn't useful, what you'd like to see, feel free to leave some feedback there. Yes, in terms of maybe before I do part 3, if anyone has any questions about anything they want to chuck in the chat or ask me now, we can do that, bit of a Q&A, and then I'll go through part 3 for those who want to hang around. So particularly anyone online, if you have any questions about anything. Or face-to-face, if you guys have any questions about the exam. Cool. Okay. So let's have a look then for those who want to stick around. If you want to head, feel free. Thanks for coming. Let's have a look at part 3, which is implementing that C program in ARM. So let's have a look at where we got. Here we go. So here's the C program. I might just go 2 columns, drag that over to here. Oops, that's not what I wanted. That's fine. You can just type it here. Cool. Oh no. Anyways, whatever. Cool. So if we if you fellas want to head, just feel free. Cool. So if we want to convert this to C, in general, like what they might give you a function that you need to implement in assembly. I think a good way to think about if they give you just like a math function is to think about what it might look like in C code and then go to assembly from there, or not even C code, just pseudocode. So don't jump straight to the assembly because you'll probably miss some of the control stuff. Try and think about how you structure it in C first, because C is very close to how assembly works. In this case, we've got the C code already, so we can just kind of jump over to doing this. So let's just set up exactly what it kind of looks like first, as in like we have this char star A. So somewhere down the bottom, we're going to have A being defined as, the world is not enough. So I should probably just chuck a DCB here. And then I can do a null at the end there. Cool, and let's just assume that's all right. So cool. I think that's all the setup that I really need to do. I need to define string 1, DCB, B is null. And then B is, sorry.
Like just define like a string that's like.
Yeah, so it just says that the following is a sequence of bytes. Yeah, so you can type as a string. You could also type as a sequence of comma separated bytes if you wanted. But yeah, you can use them to do strings. No, you would just do it like sort of like what I've done here. So I put a comma and then put the null at the end. So you would just do it like that. You can do that for integers as well for DCDs. Yeah. Cool. So I need these two strings here because I'm going to be using one of them here and one of them here. So we've got everything that we need there. Okay, so let's actually write the function. We can call this main so that that's all looks kind of neat. Okay, so let's just say that A is going to be R0, that B is going to be R1, and C is going to be R2. What I might do is I might just make them R1, R2, R3, simply because we're going to have to use R0 to get the address of A first. So what we want to do is load into R0, this equals A thing. So that's going to grab the address of our string A into, should probably do this to make it all nice, into R0. And then we've got B is equal to null. So let's go LDR R2. So we're using R2 for B. And we're going to, well, I can use a move here. Cool. And then we've got move R3 O. So, all right, and because remember that like characters are like 8 bits, so that's okay for a move here. All right, so we've got our 3 things. Let's do the loop then. So we might just say this is the loop, and at the end of it, we're going to do a branch loop sort of thing. So what are we going to do in the loop? We need to check if the value of A does not equal to null. And if it's not equal to null, then we're going to go through and do this if condition and the A++. So first things first, if we need to check that the condition is true, we need to check it at the top. So we say if the value of A, so we need to load the value at the beginning of string A into a register. So LDR, let's use R1 for this. So from R1, and we're going to load from R0, which is the register holding the address of A. So really I should put R0 there. So we're going to load that in, and then we're going to do a post increment of 1 byte. And so I'm doing this because otherwise I need to increment it anyway. Although perhaps I shouldn't. No, let's just stick to the code. The code doesn't increment it till later, so we'll not increment it. So we're just going to load the first byte. So I need to use an LDRB here, loading the first byte from R0 into R1. And then we want to do a compare. So we're going to compare R1 to 0. And based on the result, then we want to do stuff. So we want to, if it's equal to 0, then we want to branch out to, you know, I call it after or whatever. So we want to branch to after. And if not, then we want to go and do the contents of the loop. So the contents of the loop are, we need to do another comparison, check if it's equal to C, and based on that, do something else. So let's compare that value, which was R1, to C, which remember that was in R3. So we'll compare R1 to R3, and based on the result, we want to do something. So if they are equal, then we want to move the value from A into B. So move equal into R2 from R1, no, R0. Cool. And so, oops. Yeah, so we want to move R0 into R2 if the value of A is equal to C. So we did the comparison there and then did the move equal here. Cool. Last thing is we just want to increment A. So add R0 hash 1. And that's our loop. So we just kind of keep going through here. All right, in terms of our after. Now printf is a function that you are not expected to write in assembly. The question says that you can just branch and link to printf as long as you set up your arguments correctly. So we're just going to do that as well. So for these guys, we want to set up two arguments. The first is going to be a string, and the second one is going to be if we do this. So if we think about this, it doesn't really matter whether B is there or not, because if it's there and we call the first print, then it just gets ignored. And if it's there and we call the second print, then it's where we want it to be. So we're just going to set up the B to be there, and it doesn't matter if it gets overwritten by the calling function. So we need that one to be in R0, in R2, so R1 or A2, because it's the second argument to print if it is actually used. And that works really well because, oh no, that's in R2. We need to move into R1. RIP, okay. So move R1, R2. So that's just moving. So B is R2. And now we just got to basically choose whether we load string 1 or string 2 in. So what we're going to have to do is we have to compare B, which is, well, it's now in R1 and R2, but let's just look at R2. Compare R2 to 0. And if that is the case, then we want to choose the first string. So LDR, if it's equal to, where do we want to go? R0, sorry, equals string 1. And if it's not equal, then we want to load string 2 into R0. Once we've done that, we just branch and link to printf. And then we would just move, we need to make sure we just return at the end. So we move into R0 #0 and then move PCLR. Cool. So that's the entirety of that function. Does anyone have any questions about the structure? The only thing that I really think I've missed here is that I haven't saved the link register at the top. So really what I should be doing right at the top of here is I should be assuming a full descending stack, doing something like this with the link register, because otherwise it will be overwritten to the call to BL_printf over here. And then finally, I just want to probably restore. So load multiple full descending from the stack pointer, the link register. Any questions about the code there? So in terms of what goes on, try and start with like the outer stuff with the while loop. Set up how your while loop runs and kind of work inwards. And And make sure that for every time you start the beginning of your while loop, you start the end of it as well. It's similar to how you would do with braces in C. Like you don't type the first brace, type your code, then type the last brace. You type both braces and then type the code inside.
Is there a way we can distinguish between null and null terminate? But essentially, they're just the same.
They are the same thing with the exception that the null character is 1 byte rather than 4 bytes. Ideally, it's the same thing, right? It just represents 0. Null, null pointer, null terminator. It's all just the name for 0, right? But we just interpret it as an address instead of an actual value. So there's no real distinction. I can't think of a reason why you want to distinguish between the two, but that's the only noticeable difference I can see is that one's a byte, one's 4 bytes. Does that make sense? Yes. But you'll get type errors if you use a null character when trying to like actually represent a null. So yes, possibly. But at the same time, it's also very easy to do it moving 0 into a thing. And by moving 0, 0 in, like that just sets the entire thing to 0, right? So it's the equivalent of moving 4 bytes in anyway. Yeah.
Because by default, all the registers, like the general register was set to 0.
No. This is interesting because you would have noticed at the start of all of your lab programs that they were all 0, right? They're not. The person who wrote the labs wrote a little script that runs just before your ASM entry or your first line of code and sets all of the registers to 0 for you because it's nicer for debugging. In general, you can't assume that though.
But here, say we are moving we're moving a byte into R2.
Yeah.
But does that mean if we move 2 bytes into R2, then by default R2 will be like all the 4 bytes in R2 will be set to 0?
Yes. So when you do a move instruction, the entire register is set. And so I know I said that there's only 8 bits that move actually you're allowed to specify. It will 0 pad the rest of them. Yeah, implicitly. Yeah. Makes sense?
Yeah.
Cool. Okay. If there's no more questions about that, I think that was probably all I want to talk about. If you wanted some sort of practice, you can always come up with like a math function that you can think of, like the Fibonacci sequence, and try and do that in assembly. Fibonacci sequence is quite fun because it's a recursive one, right? So it becomes a little bit more interesting in how you call your function. But you can look up C code if you want to actually look at how Fibonacci works. Like it's just like int fib, which takes in a number, and then it's just basically a return fib of n minus 1 plus fib of n minus 2. And of course, you need to have a base case for if n is equal to, I think it's 0 or 1. N is equal to 1, then you want to return 1, right? So doing that one, that's actually not very complicated, right? You get probably something more complicated in your exam, but it's just interesting to think about how you would do such a recursive call in assembly. But I think the point is, for something like this, I mean, really, it looks like this, right? Int, F1 is equal to this, and int F2 is equal to that, and then you just kind of turn F1 plus F2. So try and think about it this way instead. So that's how it gets executed in C, is that like the first Fibonacci call is called first and the second one, and then you add them together. So you can always kind of do, anyway, it's just good practice to think about how you would do this in assembly. And if you're confident with that, then that should be good. Okay, any last minute questions? Otherwise we'll wrap it up there. Cool. Okay. Good luck with your finals. Have fun, and yeah, you'll have fun. Yeah.